Yeah, welcome, welcome.
Thank you.
Sorry.
Can you hear me all
Yeah,
right?
we are getting you, but the time is passing.
Yes.
So please, it's a first time we are meeting, and we are welcoming all of to you in our forum and also this symposium. Now we would like to listen from you on the global science, business, and sustainable future. But
thank you very much.
short.
Thank you.
But very short.
I'm
Okay.
really grateful to you for giving me this opportunity and giving us this opportunity. So you heard Dr. Sebastian Foucault speaking yesterday, and also
Rather, we are delighted. Please carry on.
Thank you. So I would keep it short and try to be as brief as possible. I'm currently the managing director of SPSF AGRITECH. SPSF AGRITECH is the technology company or arm of SPSF Consultancy. And Dr. Mukti Sadhan Basu, who is the founder of SBSF Consultancy, headquartered in India, is actually managing a very broad, active network of domain knowledge experts in agriculture, plus people who are experts in machine learning, data science, artificial intelligence. Because if we want to reimagine agriculture using data and make it more adaptable and adaptive and sustainable, we have to think of it as a team-based approach rather than just putting data scientists or machine learning engineers to work. We have to work together as a team with different expertise, bringing them together and taking precision agriculture forward. And this is where I will share with you what we have done so far, the ideas and concepts we would like to productionize, and how we are going on about it. So as I said, SPSF Consultancy, founded by Dr. Mukti Sadhan Basu, this company was set up in 2018 in Kolkata, India, and it is a huge network of data and data science, agricultural experts and data science experts. We started off with providing advisory and consultancy services to various companies and governments. But then very soon we realized in the process that just providing consultancy on data science and machine learning was not enough, because while the concepts have been very widely talked about, no one had a clear understanding of how you could really use it to create new products or to kind of use existing data and derive meaningful insights out of it. And that's where we started thinking that if we want to consult and if you want to kind of, talk about data, talk about machine learning, and talk about artificial intelligence, we also have to kind of create products around it that we could then hand it over to the farmers, to governments, to seed companies, to whoever our stakeholders are, so that they can see it, all these principles, all these things in action. And that's where we founded in 2020 SPSF AgriTech, which is the technology arm of SPSF Consultancy. So SPSF, what does it stand for? It stands for Science, Business, and Sustainable Futures. And basically, I founded this company along with 3 other data scientists who are, by the way, not domain knowledge experts. They come from purely data science and machine learning and artificial intelligence backgrounds. You heard Dr. Sebastian Foucault, and then I have a Spanish co-founder, Angel. He's based in Spain, lives between Canary Islands and Berlin, because now it's a global world under Corona, and everyone is free to work from wherever they are. So that gives us the flexibility. And then Manan Arora, he's based in New Delhi, and he's also a very capable and smart young data scientist. So how can AI support agriculture? And this is where I would like to quickly take you through some of the use cases that we have tackled as a company together. The first thing we looked into was pest outbreak prediction and fall armyworm, as we all know, Spodoptera frugipada. It is a devastating crop pest that is at the moment ravaging the world, ravaging most of the crops, about 300 plant species. And so we decided to look at fall armyworm and find out if there was a way to kind of make it more predictive and then prescriptive, rather than just relying on detection of outbreaks when the outbreak happened. And this is not useful in the sense because when the outbreak actually happens, there's very little a farmer can do to protect the fields. And there are evidences that have suggested that the use of chemical fertilizers and even biological control agents after infestation is not effective. I was reading somewhere that, this 2021 has been devastating for the United States of America. And this crop not only at maize, rice, and other cereals and legumes, but it also even devastated lawn grasses. So football pitches and lawns were devastated by fall armyworm. I mean, they completely chewed it down. So this is the kind of the voraciousness of the pest that we are looking at. And the female moth can fly hundreds of kilometers, about 100 kilometers a night, and lays hundreds of eggs. And it feeds this fall armyworm feeds on about 350 different crop species that we know of and counting. And FAO estimated that billions of dollars of maize was lost to fall armyworm just alone in Africa. So worldwide, we don't even have an estimate how many billions are lost. So what did we do? We used the FAMUS dataset. Now FAMUS is the fall armyworm monitoring and early warning system. There used to be a dataset, which I don't know if FAO took it down. We don't have it anymore, but we were lucky at the time we were doing this particular analysis. We found this dataset publicly available from the FAO website, and it's called the FAMUS. So what it does is it looks at field scouting, and it also looks at trap checks. So we use the field scouting data that was recorded in the FAMUS database, and there are several thousands of entries and covers several millions of hectares. So this is the data set that we used, along with world average temperature data and harmonized world soil data to kind of predictionize fall armyworm outbreak, where it would happen next. And not an alerting system based on predictive powers, not just analyzing after the event has actually happened. And we kind of, just 1 minute. Okay, so what we tried to do here, we tried to kind of assemble soil weather and outbreak data and identify the driving factors that resulted in the outbreaks and establish a model for prediction. So here, as you can see, this is a decision tree that was made using all the data sets, all the data that we used. Based on this decision tree, there were at least 14 different features that we found were extremely critical to kind of being able to predict the outbreak of fall armyworm. So this is, I'm talking about predictive modeling here and not analyzing the data. But the problem with the data set of FAMUS is the entries that were made in the data set was made on the basis of where the outbreak actually happened. So it was biased towards a positive outcome, a positive outbreak, rather than just reporting and collecting information every day, whether the pest is present or not. And this, we published this paper in Towards Data Science. If you're interested, you could look it up. And this is where we want to also take the fall armyworm outbreak prediction detection system forward by not depending only on global data sets, but actually what we realized is we need hyperlocal data. I mean, hyperlocal data is field level data that is collected from individual farmers' field, and not only when the outbreak happens, but even before. So we need a monitoring system that continuously monitors over the entire growing season and much beyond, because we know fall armyworm harbors in the adjoining crops or in the crops that grow on the periphery of the land, and they kind of And Sebastian already talked about the model crop locator. The product that we are working on using climate, land, and crop location data, germplasm data, basically, to scout for different regions for growing crops, and also that are best suited to crops, and also looking for crops that are best suited to different regions across the world. So the model maps about 160 different agroecological zones, and it's based on unsupervised machine learning model. And the reason we started off with this product is to it's a very interesting story. We wanted to optimize supply chain for a big company called Givaudan. Givaudan is a multi-billion-dollar company, Swiss-based company. They are into flavors and fragrances. And what they do is they source different flavors and fragrances from around the world, and they custom make these flavors and fragrances for different companies. So let's say L'Oreal or Christian Dior or Chanel, when they want to make a perfume, they would source the fragrance from Givaudan and then try to make it. And they were interested in one particular crop, which is called vetiver. And vetiver is native to peninsular India. Unfortunately, vetiver is no longer grown in India, and instead it's grown in Indonesia, Madagascar, and Haiti. But over the years, because of climate change, because of geopolitical situations, what happened is the cost of vetiver has increased and the supply has dwindled. And so Givaudan is looking for new areas to where they can create a new supply chain or an alternative supply chain for several of its very niche flavors and fragrances, and vetiver being one. And we used Crop Locator to identify sites in India and Uruguay that would match their existing sites in Indonesia, Madagascar, and Haiti, and thereby ensure the continuity of their supply chain of vetiver along with other crops. And this is where the whole concept of Crop Locator came into being, is to assist commodity companies to maintain supply chain security and stability. And to move on, the problem that we face, it's not the technology itself, but it's actually the data. Acquiring the data is the biggest problem. And this is where I want to talk about very briefly how Internet of Things, IoT-based devices can help us, and why agricultural ecosystems are critical. We know we can use several data, drone data we have heard earlier on, and satellite data, mobile data. Then we can use local weather stations. Plus, we can also use optical character recognitions to digitalize farm logs. And we can use many different approaches to collect data. So the technology is not the limiting factor here, but once the data has been acquired, and these are data sets that we are talking about, which are not just a few hundred or thousand data points, but we are talking about terabytes and petabytes of data. And the biggest challenge then is, how do you clean the data? How do you validate that this is the data that is related to the hypothesis you're trying to test? And then we have to go on to label what this data is for, whether it's related to a disease outbreak, whether it's related to crop performance or nutritional requirements. So then we have to label this data. And this requires a team approach. It's not just data scientists and machine learning engineers who can do that, but we need domain knowledge experts, agricultural experts. And we also need, and this is where I would like to emphasize, extension workers, the workers who are in the field, who are working very closely for the farmers. They are actually a very crucial link here between data science, machine learning, and moving towards precision agriculture. And this is, I can give you an example of the case of fall armyworm in Ethiopia. While it was ravaging the rest of Africa, Ethiopia did extremely well in managing fall armyworm. And the reason, even FAO found later on, is surely because the number of, the ratio of data scientists, extension workers to farmers. So they have a very high number of extension workers who are available to go and talk to farmers compared to the rest of Africa. And this helped them to understand fall armyworm and analyze the pest in a much better way, and therefore control it in a much better way compared to the rest of African countries when the pest outbreak happened there. And that's why agricultural extension workers are the key here. What we have been trying to do, we have been trying to use many publicly available database and also some proprietary data in building Crop Locator. So one of the database that we have been extensively relying on is the Global Biodiversity Information Facility, the GBIF database, which is free and open access biodiversity data. It has about 2 billion germplasm entries of plants, animals, microorganisms, and there are several thousand data sets that are in there, many publishing institutions and several peer-reviewed papers. So we have been using the GBIF database, but unfortunately, I would like to give you one example where you can see the results of using GBIF database and curated database. So I have been, when I was doing my PhD and my postdoc, I worked on an African legume crop called Bambara groundnut. And many of you would be familiar here with this crop, Vigna subterranea. The GBIF, using the GBIF database entry for Vigna subterranea, which was reported by, let's say, farmers or crop scientists, extension workers. So this is where it is found in Africa. And using this, we extrapolated where else in the world Bambara groundnut would be growing. So as you can see here, the map on the right-hand side is a prediction by the crop locator model, and it is all over the place. So basically, it is a broad range of locations where this crop can be grown. And we know that this is not possible because we also see some regions highlighted in North America and Alaska and other places, and this simply cannot be. So what we tried to do then is we tried to kind of go into the literature, search the literature for where Bambara groundnut has been traditionally been grown, where it has originated, where there was germplasm records. And using that data, we kind of you ran the crop locator model again, and this time it's a much cleaner prediction where you can see the intensity of color indicates the chances of that crop growing there. So the entire equatorial Africa is, of course, in this map on the right-hand side where it would grow. And so are places in India, in Brazil, and in the southern United States, where there is a high chance of this crop growing. So the point here is what we need is really curated data and very high quality data sets to be able to do any predictive and prescriptive modeling in agriculture, leading to precision agriculture. And this is what we are working on. We are trying to create this highly curated database. GBIF is a good start, but it is, unfortunately, it uses a citizen science approach where people are asked to submit entries into this database, and there is not a lot of validation and curation happening. And we know now it's impossible, almost impossible, to kind of go on germplasm exploration and start collecting from scratch all the data that we need, and for the thousands of germplasm out there. So what we could really do is use artificial intelligence to mine historical literature and produce a high quality database. And for that, we are seeking funds and collaboration to move crop locator to the next level. So if you know agencies that would be interested in supporting us, investors, we would be really grateful. Thank you very much. And thank you for your patience.